Okay, so team, in the last session, we had started algorithms section, right? So algorithms part of the course. And we started with brute force. And we said there are two different interpretations for brute force. One is exhaustive search. It means you have a search space, and each and every point in that search space is the solution, and some of those solutions are really the valid solutions. So checking each and every point in that search space and checking if it is a valid solution and then either printing it or processing it is nothing but exhaustive search. The second most common interpretation of brute force is the first approach to solve a problem, a straightforward approach to solve the problem. And we have been seeing a couple of examples in this category, right? The first approach to solve the problem. And that can be considered as the straightforward approach. And that is also searching in the search space, right? Searching for valid solutions in the solution space or search space. Okay, let's continue our journey of covering many more problems and seeing brute force solutions to them. Okay, so here is our next problem, traveling salesperson problem. It's called the TSP problem. It's a very famous problem, okay? One of the most famous problems in computer science. So what is the input and what is the output? So we are given a set of n cities, okay? So we are given a set of n cities. So you can assume that you are given a graph with nodes and edges, right? Something like this. And each edge has a weight associated with it. You can call it edge cost, edge distance, whatever. Okay, so you want to find the shortest tour through this given set of n cities that visits each city exactly once before returning to the city where it started. That means you want a tour. What is a tour? A tour is a cycle. It ends where it starts. Okay, suppose you start at a vertex A. After visiting each and every vertex, you need to end at A. Okay, so from A, you can go to one of its neighboring cities that are directly connected to A. Say you go to B. This is B. From B, you can go to one of its neighboring cities. Say you go to F, right? So on. So this is one tour. Similarly, there can be an exponential number of other tours. And each tour will have a cost associated with it. And what is the cost? It is the sum of the edge lengths of every edge in that tour. For example, A to B has some cost. B to F has some cost. F to its next node or vertex that you have selected here in the tour has some cost. So on. Add all these costs of the edges, you get the cost of the tour or cost of the cycle. And you want to find that tour that minimizes the cost. I mean, what is one simple application? Suppose you are planning for a trip, right? You start from your home. Suppose this is your home. This is your home. So you have selected, say, 6 cities. You want to cover these 6 cities for your vacation for a week and then come back to your home, right? So the distance between all these cities vary. So you want to have a good plan. So based on the distance, we will assume that the distance between two cities is directly proportional to the price, right? Or cost of the flight tickets. Cost of the flight tickets. So what do you want? You want to minimize the cost of your travel cost, right? So you want to find a tour through these 6 cities that visits each and every city exactly once. You don't want to revisit a city multiple times. And you want to make sure that you're covering all these 6 cities before returning to the city where it started, right? You want to return to home. So that's your TSP problem. Okay. Given a weighted connected graph, you want to find the shortest Hamiltonian circuit. It is also called the Hamiltonian circuit. Circuit is nothing but a cycle. See, this is a connected graph. I mean, think about if it is not connected. What happens if it is not connected? It is impossible to cover every city, right? It doesn't make sense. So it has to be a connected graph. It means if you want to visit these 6 cities, they should be connected. Okay. Next, it should be weighted. There should be weights or costs associated with each and every edge. Okay, then you call it as a Hamiltonian circuit. So you want to find the shortest such tour. Okay, so let's take a simple example. So here is a simple example. There are 4 cities, A, B, C, D, and the distance or say the cost associated with these edges are given, right? 5, 8, 7, 2, 3, right? Okay. And so we have shown all possible edges, right? And there are no more edges. Okay, now let's list all possible tours, right, that can be formed from these vertices, assuming that our starting vertex is A. So we will start from A everywhere, and we will end at A everywhere. From A, you can either go to B or C or D, right? As there are direct edges to these cities. Okay, from B, you can go to C or D. See, you cannot go to A here. Why? From B, you cannot go to A because you want to visit every vertex or node or city before returning back to A. So the number of options you have keeps on decreasing. So here the number of options you had was 3, right? B, C, D. And the number, once you selected a vertex here, the number of options will reduce to 2. So either it is CD or BD or BC. Once you have selected one of these, the number of options you have will remain fixed, only 1, right? And then you return to A. Okay, now let's see the cost. So A to B, the cost is 2. B to C, the cost is 8. C to D, the cost is 1. And then D to A, the cost is 7. So the cost of this tour is 18. Similarly, you can find the cost of all such tours. Now let's think about minimizing these costs. So which tours have the minimum costs? So this one has the minimum cost of 11, and this tour has a minimum cost of 11. So why do we have 2 here? Anyone, why do we have 2 here? 2 tours? I mean, think about it. So
it's the same path, just in the other direction. It covers all the same edges.
Exactly. So it is just the reverse of this path, right? So, and here we are assuming we are given an undirected graph. So it is kind of symmetric, right? The distance between A to D is same as the distance between D to A. It's an undirected graph, and we are considering a complete graph. What is a complete graph? If there are n vertices, there are edges between every pair of vertices. That's a complete graph. Okay, so see, if you just reverse this order, you get another tone. But it's kind of essentially the same, but you can consider them different also. Got it? So you are interested in finding this. Okay, for 4 vertices, this is fine. Suppose you have 1,000,000 vertices. What happens? How many such tores are there? Exponential number. So do you know the exact function? How many? So in fact, you can see, as I gave in the previous example, right? The number of options here were kind of 3. And then the number of options here are kind of 2. Number of options here is 1. So what is this? This is 3 factorial. So for 4 vertices, the number of tores is 3 factorial. If there are n cities, the number of tores will be n minus 1 factorial. Correct? However, we can do slightly better. See, you might have these kinds of tores, 2 and 4, which are reverse of each other, right? If you don't want to count such repeated tores, it's not exactly repeated, it's reversed. Okay, so if you want reverse invariant tores, then the number of such tores will be n minus 1 factorial divided by 2, right? Okay, so you can come up with a brute force algorithm and an exhaustive search algorithm that considers all possible such tores and find their, compute their costs, and then thereby minimizing the cost. And that takes time of theta of n minus 1 factorial. N minus 1 factorial. That's a lot. The number of paths itself is n minus 1 factorial. That's a lot, right? So can we do better? Oh, before that, so what are we computing here? The opt. So here I said opt. What is opt here? You can say you are just computing the shortest tore length, right? The minimum tore length. Or you can say you're computing the tore that has the minimum tore length. I mean, anything is fine. Okay, so this is opt. In the example, the opt was 11, right? And you know the tore associated with this cost, 11. Okay, so this is the brute force algorithm. The space required is n squared. Why n squared? The number of edges itself is n squared, right? For a complete graph. Okay, but there are more efficient algorithms. See, one is based on dynamic programming. There is something called Bellman-Held-Karp algorithm that can reduce the runtime to 2 power n squared. See, 2 power n squared. This is still better than n minus 1 factorial. See, in analysis of algorithms, we learned a lot about functions, right? And we compared functions, right? Which is, suppose you have functions f and g. What is the relationship between these functions? Do they have this relationship or this relationship or this relationship, and so on? Why did we struggle so much on finding the relationship between functions? It's majorly because of this. Suppose you have n minus 1 factorial and 2 power n squared. How do you compare which algorithm is better? You need to use that asymptotic comparison, right? Asymptotic complexity comparison analysis. So using limits and all, you can show that this is better than n-1 factorial. It is asymptotically better, right? It's asymptotically better. Okay, great. But still, these are exponential time functions. And we know that we defined exponential time functions as slow functions or slow algorithms, inefficient algorithms. Our major goal is in designing algorithms that take polynomial time. If possible, they should take polynomial time. So do we have algorithms that can compute the shortest path or the shortest tour length or tour itself in polynomial time? No. Nobody knows. This is an open problem. Nobody in the world has been able to come up with a polynomial time algorithm for solving TSP. If you can come up with such a polynomial time algorithm, probably you will get the Turing Award, right? It's that open. So TSP has been there for probably more than 100 years, but nobody has been able to come up with a polynomial time algorithm to solve that problem. Why? Because coming up with a polynomial time algorithm for TSP, if you can come up with such an algorithm, you will also be able to come up with a lot of polynomial time algorithms for solving thousands and thousands of other problems in one shot, right? So coming up with polynomial time algorithm for TSP is same as coming up with fast algorithms for thousands of problems for which no fast algorithms have been designed till date, right? Okay, so later in the last session in algorithms, that is NP completeness, we will go into details about this, why it is a hard problem and so. Okay, so that's a bad news. See, if we cannot come up with a polynomial time algorithm, now think about it. If n is equal to 100, right? What is this? 2 power 100. I don't exactly remember. What is the total number of atoms in the observable universe? Anyone? Anyone? I don't remember. It might be around 10 power 80 or something like that. Right? So it might be around this. So, I mean, suppose n is equal to 1000. So n is equal to 1000 is still a tiny number, right? It's a tiny number. So this might be bigger than, much bigger than the number of atoms in the observable universe. So what does that mean? So even for small values of n, these algorithms are not at all useful, not at all practical. So in fact, n should be very, very small. At least for n factorial, if you have an algorithm that takes n factorial, I don't think your computer can solve the problem for n greater than 25. Check that out. So try to write a simple n factorial algorithm, maybe permutation generation or something like that. That algorithm will not solve problems for n greater than 25, right? So these are not feasible algorithms or solutions for even, slightly bigger values of n, even 100 or 200. So these are not really useful algorithms. And coming up with polynomial time algorithms probably is horrendously complicated, or there might be a proof that nobody can come up with a polynomial time algorithm. Even they don't know that such a proof. then is it still a bad news? No. So there is something called approximation algorithms. See, TSP is an optimization problem. What is an optimization problem? You want to maximize something or minimize something. What are we trying to optimize here? The tour length. We want the minimum tour length, tour of minimum cost. That is an optimization problem. For optimization problems, for thousands of optimization problems, people have come up with approximation algorithms. And what are these approximation algorithms? So these are algorithms. These might not compute the exact optimal solutions. However, they compute approximate solutions. That means, look at these algorithms, right? They compute solutions, or they come up with tours whose tour cost will be at most 2 times opt. For the example we covered, if opt was 11, it will come up with a tour of length at most 22 in polynomial time. Just n squared log n. N squared log n is doable, right? Easily doable. Or you can say way, way, way better than 2 power n squared or n minus 1 factorial. And what about this? So there is another algorithm where you can get the result with at most 1.5 times opt in n cubed time. Anyway, so we don't need to learn about these algorithms or anything. I just want you to know that there is something called approximation algorithms, and these are extremely useful. I mean, think about your own vacation plan, right? Do you really care to optimize the flight cost if it takes horrendous amount of time? No, you don't care, right? So even if it is an approximation algorithm, you are okay with it, right? If it can give you the a better path, you're okay with it. And similarly, so I thought about one more. Just a minute. So even shortest path in, say, Google Maps, it's not necessary that you need to get the shortest path or shortest distance always in Google Maps. You are okay with even approximation algorithms or solutions there if it can give you quick answers. Their speed is more important, right? Okay. So anyway, so I just want you to know that there is a class of approximation algorithms, right? Class of algorithms called approximation algorithms. They are extremely useful to solve problems for which no polynomial time algorithms are known. Okay. Next, knapsack problem. So you're given n items of known weights, say W1 to Wn. These are weights and n items, and each weight, so this is one item, and its weight is, say, W1, and the value of this item is, say, V1. And you have the second item, weight is W2, value of this item is V2. So on nth item, weight is Wn, value is Vn. And you have a knapsack. You have a knapsack of capacity W, right? Capacity W. Find the most valuable subset of the items that fit into the knapsack. So you want to choose a subset of these items. And you know what is a set? It cannot contain duplicate items, right? All are distinct items. So a subset, you know, it is a subset of these items. You cannot have multiple copies or duplicates, right? Subset of these items that fit into the knapsack. What do you mean by fit into the knapsack? The sum of the weights of the items in the subset shouldn't be greater than W, right? Should be at most W. It can be less than W, but it cannot be greater than W. It should fit in the knapsack. And you want to maximize the subset value, right? So in other words, sigma Wi in the subset, right? Sigma of Wi in the subset should be less than or equal to W, and sigma Vi of the subset should be maximum. And what is the application of this? I mean, you can think about, say, a flight, right? A flight. So you want to transport a couple of items, flight, or maybe something else also, some transportation, automobile or something like that. You want to pick a subset of items that fit into that volume, or so the restriction can be based on the volume of the vehicle, or maybe the weight, max weight the vehicle can handle, or something like that. So that you can consider that as weight, volume, anything is fine. Length, right? All these are fine. And you want to maximize the amount of items you want to take. Or suppose you're traveling from your native place, India, China, or whatever, to US as a student, and you want to select a couple of items, buy a couple of items, and you want to maximize the value of that, right, within the given weight. That's your knapsack problem. Okay, so how should we solve this? And we are looking at the brute force approach, right? Brute force approach. See, here is a simple brute force approach. You want to find subsets, right? Let's find all possible subsets. All possible subsets. So how many subsets are there for a set of size n? How many subsets are there for a set of size n? Anyone?
It should be n factorial. Right?
N factorial. Okay, so let's take
2 power n.
2 power n. Why?
So like in every subset, you could either have that value or not have that value. So in every subset, you would have, for every
That's true.
element, it would be 2. It could either be the part of the subset or it won't be the part of the subset.
Very good, right? So you can choose one or not choose one. So similarly, for this, you can choose 2 or not choose 2. Not choose 2. Here, choose 2 or not choose 2. Similarly, choose 3 or not choose 3, right? So on. So if you draw this decision tree, so this is the first decision. You want to choose the first item or you need not choose the first item. So here, this is the second decision. Either choose 2 or don't choose 2. Choose 2 or don't choose 2. So similarly, choose 3 or don't choose 3. So on up till n. So there will be 2 power n subsets, right? 2 power n subsets of n items. So here also there are 2 power n subsets, right? And we have listed all of them. Okay, for all these subsets, what do? We find the total weight and we find the total value. So what is the total weight of this? The total weight of this is W1 plus W2 plus W3. So the total value of this is, say, V1 plus V2 plus V3, right? V1, V2, V4, and so on. So if we just apply all these values mechanically, right, weights and values, we get a couple of numbers. And do we have that? Okay. Oh, I didn't give the explicit example, right? Maybe that slide got deleted. Okay, so anyway, so we have some capacity for knapsack. What is it? Maybe it is 10, right? Maybe it's 10. So the capacity of knapsack is, say, 10. So all the total weights here, so if you see this, it
I
is,
think this is probably 9
is it 9?
because your optimized is 9, right?
So here there is one total weight with 10,
Yeah.
right?
But you pick 9. Look at the
Right,
fourth.
we will see that. We will see that.
Okay.
So the total weight, let's assume that K is K or W. The capacity of knapsack is 10. That means the total weight can be at most 10. Here also, it is at most 10. So all the rows that are colored, right, with light red, they have knapsack capacity at most 10, right? At most 10, less than or equal to 10 everywhere. Now what do we do? Among all these options, we want to choose that subset which maximizes the value, total value. What is the total value? Here it is 0, 42, 12, 40. What is the max number here? 65. So this subset is the answer, right? This subset is the answer. Among all possible subsets whose total weight is less than or equal to 10, this is the only subset that has the max value, correct? So this is our actual answer. Now think about the solution itself. We need to find all the subsets. For each subset, finding the total value and total weight and total value is trivial, just adding them, right? But the core logic is finding subsets. So you want to use a subset generation algorithm. Given n items or elements, you want to find all subsets of those n items or elements. So that is the core logic. And you know that the number of subsets itself is 2 power n. So what is the complexity? You don't need to find the exact complexity. You can just say that it is minimum of 2 power n. Of course, like for each subset, you need to process all the elements in that subset, right? That will be more. But the number of subsets, the number of rows itself here is 2 power n. So it will be right, either it will be 2 power n or greater than 2 power n. Doesn't matter. You can say omega of 2 power n. What does that mean? So it means it is an exponential time algorithm. Exponential time algorithm. This is your brute force algorithm, right? Brute force algorithm. But there is a dynamic programming algorithm that can solve the problem relatively more efficiently. Okay? That is not really the polynomial time algorithm. We call it pseudo polynomial time. And we will see why when we come to dynamic programming. There is a dynamic programming solution to a knapsack problem. Okay, but this is the brute force approach, finding all subsets, finding the values, taking the max. Next, let's move to graph traversals. So this is also the brute force approach, kind of exhaustive search. And you might have ideas of depth first search and breadth first search already. Where did you see these before? In trees. Remember, in trees, we covered pre-order traversal, post-order traversal, in-order traversal. You can say that all three of these traversal algorithms are like depth first search. And you also looked at breadth first search algorithm for trees. You called it level order traversal, right? So what was the other name for it? Level order traversal. Yeah, breadth first search or level order traversal for trees. That is the breadth first search here. But we will be applying it not on trees, but on graphs. How is a graph different from a tree? All trees are graphs, but all graphs are not trees. That means graphs is a much more general structure, right? Okay, so you know the basics of graphs, right? A graph is a collection. I will not go into the extreme basics. A graph is a collection of nodes and edges. Nodes and edges. Right? These are nodes or vertices, and these are edges. You might not have edges everywhere, but in the worst case number of edges is n choose 2. N choose 2. Or say NC2. What is this? This is, what is the value of this? N choose 2.
N minus 1 divided by 2.
N into n minus 1 divided by 2. So the maximum number of edges, right, is this n into n minus 1 divided by 2 in an undirected graph, right? In an undirected or directed?
Should be undirected.
Undirected. What about directed graph? How many edges you can have in a directed graph? Maximum number of edges?
We divide it by 2,
Hmm.
like NC2 divide by 2.
Do we divide by 2?
You multiply because there's just one for each direction.
Should be doubled, right? If directed. Not divide, but multiply by 2 because
Okay.
you
Should
have
we
two
divide by
directions.
2 or multiply by 2? We have two opposite angles.
Multiplied
Multiply by 2. Why?
because for every for every undirected edge, you can have like a forward and a backward. There's two different directions you can have.
Right. See, one way to analyze this is simple, right? For every vertex, there are how many? N minus 1 possible directed edges, correct? N
Yes.
minus 1 possible directed edges. So there are n of these vertices, so n times n minus 1. Here we are assuming that there are no self loops. We are not interested in self loops, right? We are not interested in self loops. If you don't assume any self loops, right, then the max number of edges you can have in a directed graph is this, n into n minus 1. In an undirected graph is this, n times n minus 1 by 2. Okay, so as you know, there are two types of graphs: directed, undirected, See, what is the meaning of directed graph? See, suppose you have this, right? See, this is a directed graph. What is the meaning of this? Assume that this is a road, a path between two cities. What is the meaning of this? You can assume that it is a one-way road, one-way path, right? This is a two-way path, two-way path. And graphs are there everywhere. Think about your Google Maps, right? Google Maps. It's a graph. From one place to another place, you want the shortest distance, or write some trips. That's a graph. Okay, Facebook. Think about your Facebook. Each person is a node or a vertex, and each friend relationship is an edge. So Facebook is a graph. So similarly, maybe Twitter and many other things. So all these social networking sites, right? They have something to do with graphs. LinkedIn is a graph, right? Professional connections, those are the edges. Okay, what about telephone networks? Telephone networks, these are graphs. What about road networks? Road networks, these are graphs. Okay, what about water pipeline systems? Right, water pipeline systems or electricity grids, all these are graphs, right? So on. There are, unlimited number of applications of graphs. So we want to analyze graphs, right? And here we might be interested in minimum spanning tree, shortest path, just the traversal, or finding the point of failure, routing, internet. How can we miss this? Internet, right? Every computer, right, is a node or a vertex, and a connection with another computer is the edge, right? Routing algorithms, right? All these are graphs, biggest applications of graphs. So we need to know about graphs. And we didn't learn this graph data structure separately in the data structures part, right? Why? Because we will learn about these algorithms here and there. So we will learn a couple of algorithms here now, and maybe minimum spanning trees later in greedy algorithms, shortest path in greedy algorithms, and so on, right? Throughout the algorithm sections. Okay, so the graph, now graph is a collection of vertices. This is the vertex set, the node set, and the edge set of edges, set of vertices. And what is an edge? Right? Edge is an ordered pair, right? A comma B. So suppose you have A comma B, it means that there is an edge between A to B. From A to B, if it is directed, and it is like this if it is undirected, right? This is a directed edge, this is an undirected edge. Okay, so based on whether you're using a directed graph or undirected graph, so you can have these kinds of, two types of edges. Okay, fine. Now, there are two major types of representation for graphs: adjacency list, adjacency matrix. And these are important. So now we are basically looking at some data structures before we move into the algorithms, right? Adjacency list. Suppose this is your graph. This is your graph. So how do you store the adjacency list? How do you store this graph? What do you need to do is you need to have, say, an array of lists. That's your adjacency list. Or you can say list of lists, array of lists, array of arrays, whatever. That's your adjacency list. Okay. So what do you have in this array? Now think about it. So how many vertices are there? U, V, W, Z. There are 4 vertices. So we will have 4 points here in this array, or 4 units or 4 values. U, V, W, Z. I mean, typically the vertices are numbered from 0 to n minus 1, right? 0, 1, 2, 3. So you can just have an array with index 1, 2, 3, 0, 1, 2, 3, something like that. Okay, so here we are explicitly showing some labels U, V, W, Z, but it can be numbers like this, because typically vertices are given indices like this from 0 to n minus 1. Okay, so from U has a list of vertices, V has a list of vertices, or here you can see that this leads to a list of vertices or an array of vertices. This leads to a list of vertices, so on. What are these vertices? E and G. Now let's think about it. E and G. Where is E? Oh, I think I made a mistake here. E and G. Okay, so look at this. U is the starting vertex. From U, you can go to V. From U, you can go to W, right? And U to V is the edge E. U to W is the edge G. So E and G are all the edges that emanate from U, that start from U, right? Make sense? So you can create this even for a directed graph, not only for undirected, you can also create this for a directed graph. So this is a generic representation, whether you're using a directed graph or undirected. What about V? All possible edges that are starting from V. What are those? E and F. E is one edge, F is another edge. I mean, you can write this as U comma W also, right? It can be a list of vertices also, or it can be a list of edges. So here they have shown edges, but you could have written it like this, U comma W. Why? Because you can go to U or you can go to W from V. Okay, so similarly from W, where all you can go to which other vertices you can go to, right? Or what edges you can take from W, F, G, H. From Z, you can take H only, right? So this is your adjacency list, adjacency list structure. Okay. The second structure is adjacency matrix. This is easier to understand. So you have 4 vertices. So create a 4 cross 4 matrix, 4 cross 4 matrix. So this matrix, you can give indices from 0 to 3, as I said before, right? 0 to 3. Now, okay, let's give this as U, this is V, this is W, this is Z. So what is E here? See, the row is U, the column is V, E is present in uth row and vth column. So what does that mean? U to V is E, right? So the idea is this: table of row comma col is equal to the edge from vertex row to vertex column. Make sense? So table of I comma j is the edge or the edge cost, edge label, whatever it can be. Maybe all details related to the edge details from vertex I to vertex j. Make sense? That's it. So how many i's are there here? All possible rows. There are n number of rows. There are n number of columns. So it is an n cross n matrix. Right? And some of these are blanks here. Some of the cells are not filled. What does that mean? There is no edge between such vertices. For example, Z to V, Z to V, Z to V. There is no edge from Z to V. Hence, Z to V is empty. Right? Okay, so on. And now think about the pros and cons of this. If you want a particular edge, if you want to know the edge between V to say W, you can get it in one shot. You can get it in O of one time. Accessing a particular edge is O of one time. Why? Directly go to that I comma j cell, you get the edge details. Very simple, dead simple, right? However, the space complexity, look at this, the space complexity is n squared. Space is n squared. However, access time for edge is O of 1. On the other hand, if you look at this adjacency list, as accessing an edge takes time, because you know you're starting from say W or something, but you need to traverse in this list to identify that particular edge, right? The traversal itself can take a lot of time. It need not be O of 1, right? You might have to traverse a lot of vertices here. Okay. However, the space consumption here, what is the space complexity? What is the space complexity here? Anyone?
O of n?
Is it n?
It's probably the number of the edges.
Right, he's right.
Is it number of edges?
Yeah, times 2. Number of edges times 2.
Right? So what is the adjacency list of this? This graph, there are no edges here.
Is it O of 1?
Is it O of 1?
No. Oh, it's n, but
Like
it's
constant
subject
space,
to.
I mean.
Yeah.
Right. So the actual total space is the number of vertices plus
Plus.
the number of edges. Right? The best case of this is n, right? The minimum value of this entire thing is n, theta of this number of vertices plus number of edges. The min value is n here. The max value is what? E can be at most n squared, so it can be n squared. It can range from n to n squared based on the number of edges. So if it is a sparse graph has fewer number of edges, then it is n. A dense graph has a lot of edges, then it is n squared. Right? See, there are pros and cons for these data structures. Hence, you choose one over the other based on applications. Okay, next we will look into DFS and BFS. So let's compare DFS and BFS. Similarities and differences. Works on trees and graphs. The time complexity is V plus E. space complex. Okay, you can leave all this. Core idea. Okay, so we will understand this probably later. Let's directly go to DFS. And let's look at trees first. Trees is simple, right? So suppose you're using DFS on a tree. How does that work? You go depth first, right? Suppose you're starting from A, you will start from A here because it's the root. You go to the left child. If there is a left child, again go to that left child. If there is a left child, go to left child again. Keep doing it, right? Once you have visited the left child, then visit its parent, and then visit the right child. So let's use, what is this called? In-order traversal, right? Let's use in-order traversal. In-order traversal. So that is like your DFS, right? See, this is your in-order traversal, right? Depth first. You go depth first. Go as
Professor,
deep as possible. Yes.
when we do the in order, the root should be in the middle, right? Is it?
Correct, correct. So when do you traverse A? After everything of this has
This is pre-order probably.
Is this pre-order?
Yeah, the root goes first. That's a pre, right? Pre-order, I think.
Oh, I see. You're saying you're processing the root.
Yes, if you process the root first, it's pre-order. If you
I see,
process
I see.
it, yeah.
See, it's actually all these three are DFS.
Yes, that's true.
Pre-order, post-order, all these three are DFS. You're going deep first, right?
Right.
So even in order is a variant of DFS. So what do you do in order? You're completely scanning this left subtree and then processing root. That's still okay, right? You went deep first, right? So it doesn't matter when you're processing the root. The core concept is, are you going deep first or not? Yes, right? So this is depth first search for trees. Whether you use pre-order, in-order, post-order, doesn't matter. It's deep first. You go deep first. What about breadth first search? Breadth. Level order traversal. Level order, right? That's the only difference. So all these three are DFS. And we have one more, that is level order traversal. Just generalize these approaches for graphs. That's it. Okay. Now, I will skip the applications. You can take a look at it later. Applications of DFS, applications of BFS. Let's go to the algorithm. So what we will do is we will mark. So what is the input? Input is a graph. Graph is a collection of vertices and edges. You know this already. What is the output? Output is the order. Order. So you can say I'm visiting W first, right? The node W first. I'm visiting V second, Z third, so on. It's an order. The output of depth first search is an order of visits for the vertices. That's it. See, I can ask these kinds of questions in the exam, right? Given a graph, apply the DFS algorithm and give the output order of this, order of vertices that are visited. Similarly, given a graph, apply BFS and give the order of vertices, right, that are visited. Simple, right? So these are the two types of questions I can ask. So if you understand these algorithms well, you should be able to solve these problems. Okay, see, mark each vertex in V with 0 as a mark of being unvisited. So that means every vertex will be unvisited, right? 0, 0, 0, 0, 0, 0, so on. Count is equal to 0. Count will be the marker, right? The visited number. Okay, for each vertex V in V, if V is marked with 0, then DFS of V. So what is it saying? For each vertex V in V, suppose the vertices are numbered like this: V1, V2, V3, so on up till Vn. If V1 is marked with 0, if V1 is marked as 0, then DFS of V1. If V2 is marked as 0, then DFS of V2. If V3 is marked as 0, then DFS of V3. So on up till if Vn is marked as 0, then DFS of Vn. That's the meaning of lines 3, 4, 5. Make sense? 3, 4, 5 really means this entire thing. But why should we do it? Right? We will analyze it later, once we understood these DFS code itself. DFS of a vertex V, what does it mean? Right? Let's look at DFS of a vertex V. You are given a vertex V, you want to run the DFS algorithm on this vertex V. Let's see what that means. We will assume that count is a global variable, right? That means it is accessible directly. Okay. Count is equal to count plus 1. We increment the count and we will mark V with the count. We will mark V with the count. Mark V with the count. And then we will see, look at this. Look at 3, 4, 5. For each vertex V, W in V adjacent to V. That means look at all the neighbors of V. Suppose there are 5 neighbors. Suppose this is W1. Suppose this is W2. Suppose W3, W4, W5 are neighbors of V. What do you mean by neighbors? That means from V, you can go to W1 directly via an edge. From V, you can go to W2 via an edge, and so on. These are the neighbors of V. What do you do? If the W is marked with 0, if it is marked with 0, it means it is unvisited. If it is unvisited, then do DFS of W1. If this is unvisited, do DFS of W1. If this is unvisited, do DFS of W2. If it is visited, you don't need to visit it again, right? DFS just means visit all the vertices from this vertex or whatever. If it is visited, I mean, you don't need to care for it. If it is unvisited, only then you will recursively call this W3, so on. Make sense? That's the logic of lines 3, 4, 5. Okay, lines 3, 4, 5. So keep this in mind. We will look at an example to understand this better. So here is your graph. What do we finally want? We want the order of vertices that will be visited through this algorithm depth first search, right? The input is this graph. The output is just an order of vertices. So we will start with, look at this, for each vertex in V in V. So we will assume that all these are lots of vertices, right? We will go in the alphabetical order. That means this is the first vertex, B is the second vertex, C is the third vertex, and so on. Okay, so we need to start with A, right? We need to start with A alphabetically first. Now look at this. From A, no, let me go back here. From A, what happens? Initially, everything is unvisited. You're marking with 0, that means everything is unvisited. Every vertex is unvisited. If it is unvisited, call DFS of B, right? So we will call DFS of A. We will call DFS of A. Okay, let me. So mark this. Okay. So initially count. Let's go back to the code again. So remember this code. If V is marked with 0, DFS of V, that means DFS of A will be called. Count will be incremented. Mark the vertex with the count. Okay. So DFS of A will be called. The count will be incremented to 1. We will mark A with 1. Now that means A is visited, right? A is visited. Now, in a loop, what are the neighbors of A? B is a neighbor of A. F is a neighbor of A. E is the neighbor of A. We will go in the sorted order, alphabetical order. So we have, let me show here, A. Should I write here or here? Maybe I'll write it here. A, the neighbors are B, E, F. We'll go in the alphabetical order only, right? B, E, F. Okay. Now look at this. For these are the neighbors of A. If that neighbor is unvisited, visit it again. So B is unvisited. So call DFS of B. You call DFS of B. Increment the count. Mark B as 2. Right? So this is 1. Mark B as 2. And look at all the neighbors of B. What are the neighbors of B? A is a neighbor of B. C is a neighbor of B. F is a neighbor of B. That's it, right? But A is already visited. We don't care for A. So A is already visited. We don't care for A. Right? A is already visited. Next, what are
Professor,
the
can I ask a question?
Yes, yes.
Real fast. So this is depth first. I would have expected you to go down to E first instead of going across to B.
No, B is also the neighbor of A, and B comes alphabetically before E.
Okay, so I understand that. I guess to me, depth was just going down the graph first, but I guess you're
so
saying
depth,
it doesn't matter.
Okay, so depth doesn't mean, structurally depth, because now think
Okay.
about this. For example, suppose I have X, Y, Z, right?
Right.
You can also write this as X, Z, Y, right? The same graph.
Yes.
Now, which is depth here?
I was just thinking, down along the longest dimension is what I was thinking.
So what about, see, this is also the same graph, right?
Okay.
So the same graph can be tweaked left and right in any orientation. So depth doesn't mean this depth, the physical depth. The depth here is in the child relationship.
Depth is in the child relationship.
See,
Okay.
B,
So the
E,
one
F
that has the
are
most
children.
children.
Right. B, E, F are children.
Right.
You go into one child and go into children of them, right? And one, grandchild, so on.
Okay.
And then finally, when you have completed the entire tree of B, then you go to the tree of E.
Okay. Okay. I see.
That is the meaning of depth here.
Okay.
Okay.
Okay. Thank you.
So now, what are the other neighbors of B? C is a neighbor. Then what?
F.
F is a neighbor. Good. C is unvisited, right? C is unvisited. So expand C, that means you will be calling DFS of C. You will mark C as 3. See, the first node you visit is A, the second node you visit is B, the third node you visit is C. What are the neighbors of C? B, D, G, right? B is visited. D is unvisited. So what do?
Mark it with 4.
You call DFS of D. Now expand D. If you expand D, okay, you visit D, right? So you mark it as 4. Expand D. If you expand D, what are the neighbors? C, G, H. C is visited, right? C is already visited. 3. C is not 0, right? C is 3. So C is visited. What about G? G is unvisited. Expand G. Make sense?
Yes.
You are going deep in the child relationship. Child of child, child of, right? You're completing the subtree of one child before moving to another child. That's the meaning of depth first. That's it.
Okay.
Okay. So let's also go to the next slide. See, it will show you the order A, B, C, D, and G. Correct? That's what we got here. That's exactly what we got here. D, and then G. G is the 5th vertex to be visited. Make sense?
Yes.
From G, what do you do? What are the options you have now? You have C, you have J, K, L, correct?
Yes.
But C is visited. So that's why they showed like this. C is visited. You cannot revisit it. C is visited. So next.
You also have D, right?
Right, you're right, you're right, you're right, you are right. You also have D. D is also visited. Right?
Yes.
All these are the neighbors, but some of these vertices are already visited. So you cannot go to C, you cannot go to D, you have to go to what?
J.
J. That's your next edge, vertex that would be visited. J is 6. Right? Okay, now I will stop writing. You got the idea of the tree, right? See, let's try to do it in a fast way. G, okay, 1, 2, 3, 4, 5. Next is, so try to visually find the order in which they are visited, right? Visually. Okay, next 5, then this should be 6, correct?
Yeah.
Okay, so next, what are the
I?
Is it I? Yes,
I think so.
7. Okay, then
E.
E.
Is it E? Okay, great. 8.
Then
Then
F.
in among the neighbors of E, what is the alphabetically first that is unvisited?
F.
F. 9. Good. And then
You go to M.
wait,
No,
wait.
no, you're done.
No,
You're done
what
with that tree.
we are done with F.
But
F does
then you
not
go back
have
to
any neighbors, right? Neighbors that are unvisited. So what do we do? I mean,
You
tell
go back
me
to
at this
I,
step.
right?
No, at this step we don't go to I.
No.
What do we do
Okay.
at F?
You go to E.
You go to the parent, right? Parent who called you. When you don't have any options left, you go back to the parent who called you. Who is the parent? E. Now, so check if there is any neighbor of E that is unvisited. No. Right?
Neighbor or children?
Neighbor or children,
Neighbor.
both are same here.
Okay.
Right? Because you're trying to
Oh,
expand.
yes, yes, yes. Okay, sorry. Yes.
Right? Okay. So is there any neighbor or children of E that is
No.
unvisited? No.
No.
So what happens now?
Then you go
What-
back to I, right? I,
Right.
its parent.
The program control goes to its parent node, that is I. Now, is there any neighbor of I that is unvisited?
Yeah. Mary, M.
M, right? Why not N?
Alphabetical.
Alphabetically first, right? Let's go to M. This is 10,
10.
right? So
Yes.
neighbors of unvisited neighbor of M next is
N.
11
11, yes.
for N, right? Okay. Next, unvisited neighbor of N.
K.
Okay. K. Then
Then O.
unvisited neighbor of K. Okay. Then
You go back to G eventually, right? Because everything else has been
no, at
visited.
this time what happens from
You-
O?
You go back to K.
You go back to its parent K.
K go back to N.
From K, there are no unvisited neighbors.
Yeah.
You go back to its parent, that is N. So
And
who is
go-
the parent of K? Is it J or G or N?
K's parent is N, just N, because
Right.
you look at the order 11, 12, right? So
Correct. The order in which you can also write a tree, right? If it gets confusing, you can write the tree also, right? Okay. N, from N
you go back to to Mary, yeah,
back
M.
to M, and then back to I, then
You go back to J,
J, then
L.
G. G,
from
you go to
J,
G.
you
G.
go to G,
Yeah.
Right.
then
You go to L.
You go to L.
Yeah.
L. Okay. So from here you go to L. So what will be the number?
14.
14. Okay, from L,
You go to H.
right. Unvisited neighbor of L, alphabetically first, that is H. And then
P.
you
Final.
cannot go to anywhere else from H. So you go to the parent of H.
Back
And
to
the
L.
next neighbor of L is P, right?
Yes.
That's it.
Is this correct?
Yeah, so that's just basically a stack, right?
Correct, exactly. So you need to, I mean, you are implicitly using a stack here because as we saw, right? Recursive algorithms implicitly use a stack. See, look at this order, whether it is correct or not. G, J, I, E, F, and we have shown some edges where we cannot go there because it's already visited, right? And then from I to M, N, K, O, we reached a dead end, right? Then we backtrack to K, N, M, I, J, G. From G, we go to L, H. We cannot go further. Go back to L and then go to P. Is this correct? That's your DFS. Right? So what do you need to write as output? These sequence of vertices. Okay. Make sense? So team, does this make sense?
Yes.
Okay, so this is the DFS algorithm. You know the input and output. Okay, so we are running out of time. I wanted to complete this also. Anyway, so we will increase the pace from next class onwards, right? So try to prepare these slides and these topics beforehand. We will increase the pace and have a list of all the questions you have to, right? Because I think we are lagging behind and we need to increase the pace. Okay, so any questions till now? See, let me show you of one or two applications very quickly. See, let's take this, finding connected components. You can use DFS to find connected components. What is a connected component? So a graph can be considered as a collection of connected components. See, so all these are all the nodes are connected here. There is a path from one node to other nodes here. They're connected. But you cannot go from one node to here to a node till this point because there is absolutely no connection. Right? This is a different connected component. Suppose you want to find these clusters of nodes, right? Clusters of connected components. How do you find it? Think about Facebook. I mean, you can have a Facebook like this, right? There is a friend group who are not friends with anyone else, right? There are 4 friends who are friends with themselves and they are not related to anyone outside. So that's a connected component, right? Suppose you want to find such connected components. You can use DFS. Think about how, right? So think about how you can do that, right? This is one very simple application. So similarly, you can look for other applications also, though this is out of syllabus, out of scope, but it's good to know more, right? Okay, we will stop here and we will continue in the next session. So try to prepare and come because I'm going to increase the pace of this. We want to cover a lot more topics. Okay. So any questions, team?